I think maybe it's time to start. Looks like most people are here. So welcome to the first academic seminar of the series. Before we get onto the presentation, to get those 15 PEP hours, attend at least 5 talks, complete the sign-up form, log into your Zoom Uni account, and complete the final feedback form. For more info on PEP requirements, visit our website. It would be great if you could turn on your cameras as well to make Francois feel more welcome. Apologies in advance if I mispronounce your name, but today we are joined by Dr. François Guillard, who will give a presentation on crunchy matter from breakfast cereal to sinkholes. François is a lecturer at the School of Civil Engineering at the University of Sydney. He has received his PhD in 2013 from a university in the south of France. His research is aiming at understanding the behavior of granular materials and brittle porous media such as sand and puffed rice from experiments, numerical simulations, and modeling. I'm sure you're all intrigued to learn about crunchy matter, so I'll hand it over to François.
Thank you a lot, Sinjita, and the pronunciation of my name was perfect, so I don't know I can pronounce yours as well, but I think I will try. So thanks a lot for the invitation, first of all. It's great to see so many people, and I think it's been a long time that I haven't talked to 206 people at once. So I didn't really know which level to pitch the talk to, so hopefully there will be a bit of broad level for anyone to get something out of it. So let me share my screen first. All right, so hopefully everyone can see that. As you know, so I'm François Guillard. Hello, everyone. So today I'm going to talk about crunchy matter from breakfast cereal to sinkholes, which is kind of a funny title, I guess. As you can see on this slide, it's actually a work that has been going on for quite some time now, probably 6-7 years now. And that has involved a lot of people. So most of the most important are on this slide. And in particular, I want to thank Leonardo Crespo-Parga, who provided quite a few of the slides towards the end. So it's a lot of the work of the 2 PhD students that we have right now on this project, which is Leonardo and David Riley. So I wanted to mention that from the very beginning. All right. So what are we talking about? So we are talking about brittle porous media, which is basically a very wide class of material, actually. A lot of material, natural or artificial, are brittle porous material, which means, so porous, it means that they have pores inside, so they have some void, or usually filled by air or water within the material. And most material, of course, are brittle. If you put enough force on of them, eventually they will break. That's pretty much what that means. And so we can see here a few examples of natural material, and because as you may have seen, I'm from the geotechnical or geomechanic group, so we are dealing a lot with natural materials such as soils or rocks or things like that, and these are really archetypes of brittle porous media. Snow is also a very common example, of course. You've all seen how snowflakes can break very easily. But it's also materials that are very common in industry, not only in the building industry. Sand is a very widespread, a very important material, of course. But pharmaceuticals as well, pills that you may have, for example, are usually formed starting from powder, which are compressed and compacted. And a very wide range of materials, such as metallic foam, like we have here on the right. So really a broad range of material. And one of the things that this material have in common, and at least that's kind of what I'm going to talk about in this talk, is the fact that because they are brittle, when you compact them, they can form this kind of inhomogeneities that you can see very clearly in the foam here. The foam, like when we compressed it, instead of compacting homogeneously, we see that the foam has buckled on itself in a very well-defined defined area. And if we keep pushing, this area is basically going to grow, and this compaction band, as we call them, is going to grow. And we can see the same thing, obviously, in the picture at the top. For example, the middle one is very clear. Well, this rock has been compacted by geological forces, and you can see these areas of much higher density, so these compaction bands that we see here. Same thing with the snow. Of course, as the snow keep falling, the layer of snow keeps increasing, and the grain at the bottom gets crushed more and more. And this has quite a few consequences, if you think about it, because it means that the material is no longer homogeneous. Right, so it means that if you are trying to pass a fluid through it, if you have water and things like that, the behavior of the material is going to be very different between the zone where there is a lot of compaction and the zones where the material is looser. And the pharmaceutical example with pills is very clear, right? If during the process of forming your pill, if you have compaction bands like this one in the pills, it means that some area will get dissolved in the body differently than others, and then you can have a poor delivery of the medication, and this kind of issue that can arise. So that's kind of the broad idea, right? That this porous media can exhibit compaction, inhomogeneous compaction, and we are trying to understand that, to prevent it if we need to, or to just to understand and to see if it has an importance on the mechanical response and this kind of question. Now, as I said, I'm in a geomechanical group, so we are looking at soil and sand and things like that. The trouble is this kind of compaction, like you see in the rock here, they take a very, very long time, right? If you think about tectonics, plaques and things like that, if you think about convergent fall like this one, obviously the motion are like millimeter per year, something like that. They happen underground, so really there's no way to track the material or to really get a good grasp of what is happening underground. And even if you take the material, bring it to the lab, well, it's also very stiff material, very strong material, right? Most rocks at least have very high strengths. Most soil, most sand have very high strengths of the grain themselves if we are trying to break the grain. So experimentally, it's not that easy to work with this kind of material. So one way to address this issue differently is to go to a different material that will be a model material that will share some of the characteristics, at least, of the material you are trying to model, but that will be easier to handle, and that will simplify the handling experimentally. And so one of these material, I mean, you probably have guessed it from the title, is puff trice, right? Because puff trice is, well, first of all, very easy, very available, and it's also very easy to break. I think everyone has been able to break a grain of puff trice in the morning. It's very weak, so really there's not much force required. So it means that the equipment you need to compress them is very simple or very cheap in a way. And yeah, so it's very convenient, and it has a lot of texture, so you can also do quite a lot of analysis from this to try to get really some interesting behavior and interesting insight into the material. So okay, so let's look at what that gives, right? So we are going to do a very simple experiment here. We just have a cylinder full of puff trice, and we are just going to come from the top, compress it at constant velocity. And what we'll do, we'll measure the force at the top. So what's right? So we have a load cell at the top that just measures the stress that we are applying at the material. And because we are taking images, we'll also be able to, and the container is transparent. So we are also going to be able to measure the velocity of the material at any point along within the material, effectively. And we are doing that dry, so that's kind of the experiment at the beginning. One thing that you will see in the movie in a second is that, so I have a couple of graphs on the right. The one at the top is the stress as a function of time. Okay, so just the force that I'm applying at the top as a function of time. And the second graph is something that I show quite a few times in the talk from now on. So I want to explain it a little bit. So it's called the spatial temporal graph because it has space in the vertical axis and time in the horizontal axis, right? So the vertical axis corresponds to space. So 1 is the top, 0 is the bottom of the sample. And basically what the color mean is the velocity along a line at the center here, right? So if we look at the color, the white is high velocity, so pretty much the velocity of the piston here, and black is going to be 0 velocity, right? So basically this graph shows at every single point in time, what is the velocity of every point along the center line here of the sample. Okay, so let's look what that gives. So let's do a compression. Okay, so initially, I guess not too much is happening. We're just pushing on the material, and yeah, it just compress. But what you may be able to see, I don't know how much you can see it through Zoom, though, but hopefully, what you can see is that eventually the material breaks, or the sample separates into two zones. Then there's one zone that is pretty much static at the bottom, and one that is moving at the velocity of the piston at the top. And the boundary between the two zones is moving from bottom to top. So maybe the arrows are going to help you, but you may be able to see this, this band that is traveling through the material in this movie. Right. So basically what that means is that the material by itself has decided in a way to split into two zones, one that is moving at the velocity of the top plate, and one that is pretty much static. And because we keep compressing, of course, the boundary between these zones has to be traveling through the material. And so we have this compaction band, as I was saying, that is traveling through the material. So it's a bit different from what we have seen before. Although before it was if you remember the rock here, it was static, but we don't know if the process itself was static, right? It's just a snapshot that we see at one point. Now here we see that we have a dynamic process that happens in the material as we compress it. Now again, we can go a step further and say, well, that's one experiment, but it is still a little bit inconvenient in a way. Needs quite a bit of material. We need to go buy Rice Krispies calls every 2 days. It's a bit annoying. So the other aspect is that experiments can be tricky. There's a lot of parameters that you don't control. So a good way to complement experiment is to also do numerical simulation. So in numerical simulation, basically you are assuming a model for your material, and then you can do effectively a simulation that will give you some kind of response. You need to be careful because, of course, it's still just a simulation in a way. So you will get out what you put in a way. So if you are making assumptions that are completely wrong for your material, or if you are not doing the simulation correctly, then you will get pretty much random thing, as people say in a numerical simulation, garbage in, garbage out, right? If you don't get the model right, then things are not going to be great. But it's a good way to complement experiment, as I was saying. And it's also a good way to explore a broader range of parameters. So let's try to do that. So the way we do that, it's very simple. Here we just consider that we have a rectangular array grains or of materials here. And in this grid, the material points in a way are connected by spring, and these springs are able to break. So that's where we put the properties of the material. So if I have a spring here, you can see if the length of the spring decreases, eventually I have a maximum force that the spring can handle, and then it breaks, and then it can do that several times, because if you try to contract a Rice Krispies, there's a lot of pores, so each of them can break one after the other. So that's very simple model, very simple geometry. We are in 2 dimensions, so nothing too fancy here. So we use this model, compress it, and what would you know? Of course, if I'm showing it, that's because it kind of works. Basically, the numerical model is able to reproduce the same kind of instabilities that we have been saying in the first in the experiment, right? So that's the plot at the middle. The one on the left is the experiment that I just showed you before, and you can see this very simple numerical model just with springs that can break basically reproduce the same kind of separation of the material in these 2 compressive zones. Now, what's interesting is that the behavior is even richer than that. Because if you go to very low velocity, you can see here that this compaction wave pretty much disappear. This oscillating compaction pretty much disappear. Then you have some random breakage. So the material breaks once in one location, and then sometimes later breaks somewhere else, and it's not correlated. On the other hand, if you go very fast, that's what you see here at the bottom. Basically, the material compacts as if it was not breaking at all. So there is a lot of breakage inside, but you can't really distinguish this kind of compaction from if you had just an elastic medium that was compressing. So that's kind of interesting, and that's a very wide range of behavior. And that's again, if we relate that to other material, of course, that's important, because it means that depending on the range of velocity or of the range of regime we are looking at, then it's going to behave very differently, and other materials are going to behave very differently. So how do we characterize that? I'm going to skip that. I'm not going to show too much equation, don't worry. But basically, the typical way to characterize this kind of behavior is to do a phase diagram. So we look at, okay, so what are the characteristics of our material? What are the characteristic time, for example, in our material? What are the things that really characterize the behavior? And so if we do that, there's basically only 3 times that you can come up with. There's one that is basically how often are our springs breaking, right? So are they breaking every second, every 100 seconds, every year, this kind of thing. So that's the first one. The second one is one that I think all of you should know, which is elastic time, which is basically linked to the speed of the elastic wave, right? So if I have an elastic wave that travels through my material, so like sound or something like that, how long does it take to go through the whole material? And the last one is viscous time, which is simply how long it takes for a material point to slow down under viscosity. So really, that's the 3 characteristic time, and as I said, now we can compare them, and we can see, okay, which one is dominant, which part of the phenomenon is happening the fastest or the slowest. And the typical way to do that is to build non-dimensional numbers. So that's the same kind of concept that you have in fluid, I guess. Capil is here, so I have to mention fluid. With the Reynolds number, right? The Reynolds number is a non-dimensional number that characterizes the behavior of your fluid. We can do the same here, except because there's 3 characteristic time, we'll have two non-dimensional number, and we can plot them in this kind of graph. So we have the ratio of 2 of the time on the vertical axis here, ratio of 2 other time here on the horizontal axis, and at each point we show, well, what is the behavior at that point. So the way we can read that, we can go a little bit into the detail of the graph, but we can say, okay, so if we are here on the right, it means that we are breaking not often at all. Like we are almost never breaking. It takes very, very long to break. And at the same time, our viscosity is probably pretty low. So it does mean that we break at one location, but the information is not carried away, because when we break, the grain immediately slows down because of the viscosity, and then that's it. Nothing else happens. And at some point, as we keep compressing, somewhere else is going to break, but there's no link with what was happening before. On the other hand, on the left side here, we are breaking very, very often. We are actually breaking so often that really the viscosity has no time to do anything and to slow the grain. So we are breaking all the time everywhere. So that's why we have this homogeneous compaction that I showed before here, right at the bottom here. We are going very fast. We are breaking everywhere all the time. Really, our material is homogeneous at that point. And then in the middle, it's actually where things happen, where we have this kind of oscillation compaction, because we have this balance between the different regimes. So that's basically the whole idea here. We have all this different regime of behavior that happens in this puff dries. Just from a very simple experiment of one-dimensional compaction, we have all this kind of behavior. All right. So now the question is, I guess, okay, so we have this behavior, but really, where does this instability come from, right? There's no real reason for this instability to develop, because if you think about it, because I mean the material is homogeneous, so why do we suddenly have this instability that develop and that completely break the homogeneity of the material? So just to give you an idea of that, a lot of these instabilities actually happen when you have softening in your material. So just conceptually, if you think about material, you probably have seen a lot of materials that are hardening. So basically, the faster you go, the higher the force in your material. So again, if we think about a viscous fluid, that's typically viscosity, right? Viscosity, if I try to move faster, the resistance force from the fluid is going to be higher. If you have tried to swim, the faster you try to swim, the harder it gets. But not all materials are like that, and there are quite a few materials that actually, in some range of parameter, exhibit softening. So what that means is that instead of the force monotonously increasing with velocity, we have a region where the force actually decreases as the velocity increases. And that has quite a lot of consequences. And in particular, that's a very good way to start instabilities. Or good, I don't know, but it's a way for instabilities to start. Because if you think about it, if you are doing a force control experiment, or if you are trying to increase the force on a material that has this kind of response, right? I increase the force, okay, but eventually I will reach this point here where I have a maximum in the force, right? So I won't be able to increase the force while keeping the velocity increasing monotonously, right? Because I can't keep increasing the force here with the same velocity. So the only way for the material to react at this point is to jump basically on this side of the curve and now say, okay, so I can't keep going at this force at this low velocity, so I will actually jump to a much faster behavior. And if I keep increasing the force, the velocity will just keep increasing now. And so that's an instability, right? Here I am moving at low velocity, and I just have to have a small increment in force, and I am jumping to a significantly higher velocity. And of course, the behavior is just reversed in the other direction, but you see, you actually end up with an hysteresis here. So the behavior is not completely it's not a direct reversal of the behavior. So that's really very broadly how this kind of instability works. And there's one that I actually want to try to do an experiment here, but I don't know how if that is going to work, because it's a very typical experiment and a typical instability, which is called the stick-slip instability. So with friction, you can do that very easily because static friction typically is higher than the dynamic friction. So if you try to push a block, you will often end up with this stick-slip instability. So let me move quickly to do this, and hopefully. All right. So it's not the best setup, but you know, we are working from home, so that's pretty much how it gets. So basically, I'm just going to do if this is working. Yeah, okay. So I just have a spring here, right? So that's just a simple spring and just a block here. Don't forget about the power cord. It's just what I had at home. Okay, and so what I'll do, I will push this block I will try to push it with the spring at constant velocity. And what you should see is that nothing is moving, and eventually the block move all at once, right? And so you see, so basically the block is sticking most of the time, but when the force reaches a certain force, it starts moving, and because of this, so it's an instability, and so it moves and eventually goes to a rest. And again, that depends on the velocity. So that's exactly the same thing as before. If I go fast enough, I can actually move this block at constant velocity pretty much. And I think I need both my hands to do that. But you see, if I push fast enough, well, with the lag of the camera, it's a bit harder to see, but it basically moves at constant velocity. So that's a very common phenomenon, as I was saying, that happens everywhere. It's even you can even see it in metal. You have a similar kind of instability, and again, that's quite important in metal in particular, if you think about it, because it means that the stress that your metal can resist or that it can carry is going to be very jerky and very inconsistent. So obviously that's not the best response for material, because you need to consider that if you are relying on the force in this piece of material to carry any load at all. So okay, so that's all well and nice, but is that how Rice Krispie behave, right? Because that's our main question. Is it actually does puff rice actually have this softening effect? And again, since I'm showing it, that's because it works. Yes, we do have this softening effect. So here, if you look, for example, at the red curve, so that's simply so we are simply same experiment. We are we are controlling the strain and measuring the stress at the top, and we are changing the velocity at which we push. So the numbers here are sorry, I should have the unit is in millimeter per second, I believe. And you see here, so if you follow the red curve, for example, when we reach this point, we decrease the velocity, and you see the stress jumps at a higher value. And then we increase the velocity, the stress decreases, and then we increase again the velocity, and the stress decreases again, right? So that's exactly the behavior that we were seeing here, right? We are kind of here in the middle of this decreasing side. If I decrease the velocity, my force increases. If I increase the velocity, my force decreases. Okay, so that's basically the idea. Because we have this softening in our materials, in our puff rice, we are actually seeing this kind of instability that appear in the material. All right, so I'm going definitely a bit slower than I expected, so maybe I'm going to keep going. So that's that's basically what I wanted to say about this kind of constant velocity compression. So that's what we have been doing all the way to here, right? We have been controlling the velocity of our material, and eventually we break it, because if we control the velocity, the stress, there's no limit on the stress, on the rise of the stress, as long as our machine is working, and at some point the material is going to break. But now we can do something a bit different. A lot of situation in industry and in general are actually more stress control, right? So if you have if you see at the bottom here, if you have a dam, a dam here, the dam is creating a stress on the soil below, right? It's not creating a velocity; it's creating just a certain. It has a mass, so it creates a stress on the soil below. So in this case, well, basically, if we apply a constant pressure, and it's below the strength of our grains, then nothing happens, right? My grains are strong enough to handle the load, and nothing happens. Well, not quite, right? Because like things can evolve over time, right? So there is like our grain can get weaker, for example. And if you think about it, that's a reasonable assumption, right? If I have a dam or something, or some structure, then I can have water infiltration. I can have a lot of process that may weaken the concrete or the material that is or the soil that is there. And in that case, if I weaken my material, eventually I may actually get to a point where my material is weaker than the load that I'm applying, and now my material is breaking. So that's what we are going to consider now. So of course we turn back to our favorite material, the puff rice. And as you all know, when you put milk in puff rice, the puff rice gets softened and gets weaker, and eventually gets all mushy and weak. So that's exactly what we do here. We just take our puffed rice and inject milk at the bottom and see what happens. So we just inject a certain quantity of milk, and we just look at what happens. So that's what this movie is doing. I'm just so that's quite macro video here. So you can see the grains are pretty big because we are pretty zoomed in. But so we inject the milk at the beginning, and you see the grain, and we are under constant load, right? And so you can see the grains are all mushy at the bottom here. But what you can see is the grain at the top. So just moving the camera a little bit, you see the grain at the top. They are actually not moving consistently inside the mushy part here at the bottom. You can see that you have this kind of dirty flow again, where basically all the grains above just move at once into the material. And so yeah, so it's not an artifact from the video. If you see it in the slide, it is actually the physical phenomenon. And so what you may be able to see here is that also the rate of these drops is actually decreasing, right? So it's you have much less displacement of the grains at the top here than you had at the beginning. So that's quite a funny one, I guess. And what's quite nice is that we have injected a very like a constant amount of water, and then we just leave it there at constant load. And you see that these drops that we can measure on the stress again at the top, these drops actually happen over many hours. So you can really follow the grain, so keep the experiment running, and just see this grain going slowly into the material in a very consistent pattern over hours. And again, you see, as I mentioned, that the rate of these drops slows down, right? So you have less and less of this drop as time goes by. So we can just have a look at it. We won't go into too much detail in that, but if you look at the time between the drops as a function of how long you have been waiting, you can see that you have this very nice behavior that again we can model fairly nicely, and it works pretty well. So we can explain how this happens and how this behavior emerges from the wet puff rice. All right, so now in the last part, I just want to get back to a bit more real material, I guess, because now we have an understanding on how we can generate this kind of instability, right? We know that if we have a weakening mechanism for our grain, then we are usually able to see this kind of instability developing. And that's quite interesting because every material you can find a way to weaken them. So, for example, I'll just show in a second the ice and the calcareous sand. It's quite clear in ice you can probably let it melt, and eventually that should kind of shrink the grains and make them weaker. Same thing in calcareous sand. You can probably dilute it in acid or have some kind of chemical reaction that are going to affect the strength of the soil. And again, that's exactly what Leonardo Crespo-Paraga is working on. So all of the slides pretty much from now on are his. So the first thing I wanted to mention is about ice. So let's do a pretty much similar experiment. So we put ice in a container here. We put some load at the top, and we observe. We look what happened, and we hit from the bottom a little bit just to let the ice melt. So the time is in minutes here, and what you can see is that we do have this kind of instability developing again, where the ice is actually, our ice bath is not melting homogeneously, and we don't have like a consistent compaction of the material. We just end up with this kind of creep period here, followed by really drop in the top plate. And this, of course, is it's very important because I mean, we all know that global warming is really I mean, a global issue, right? And a lot of the sea level rise is due to ice shelves melting in onshore. So glacier melting and Greenland and Antarctica melting of the snow cap there. And what that means is that there will be, like if this kind of instability develops, you can have a feedback between, between the rate of loss of ice in a certain region with what is the dynamic of the material and of the ice. That's actually something that I wanted to mention, is that that's actually something we have been looking at with a group of honors students last year, I believe, where we link, where we have been able, from seismic data, we have been able to show that this kind of instability exists, and to relate that with other phenomena. The last thing is that I wanted to talk about is calcareous sand. So if you take a sand that can react, so for example, calcareous sand, I mean, maybe you have done this experiment or this demonstration in class at some point. If you take a block of calcite or calcareous material, you try to put acid on it, so vinegar or lemon juice or something like that, or Coke is also a fairly common fluid. Then you see bubbling and you see gas production, and that's because the chemical is attacking the material, and it's chemically reacting with the material. So that's something that, again, we can do in experiments. So we have our material here. We put constant force on top, and we flow vinegar within the material. And so that's the video on the left. If you do that, you can see, so you have bubbling because you're producing CO2, basically. And again, you can see instead of continuous compaction, you do have this kind of quakes that happen. That is this jerky or irregular compaction of the material. And again, that's of course this is a laboratory experiment, so we can always say, oh, that's maybe it doesn't have that much application, but a lot of structure and a lot of industrial situation can have this kind of effect. So if we think about tailings dam, for example, so this is basically mine storage facility for in mines, which get wastes. Wastes where the waste material from the mine is stored, and a lot of this material is actually can be fairly reactive chemically, and they require long-term storage, right? Because even after the mine is closed, you do want these things to be safe, and they do fail. They do fail. So and there has been quite. I mean, when they fail, it does have quite a lot of consequence for the environment, in particular. Not to mention human life if there is if there are some around, but this can really affect the environment, because it's a very reactive fluid that is released. And so better understand how we have this intricacies or between the reactive fluid and the dam material. It's very important for the long-term stability as well. And I promised sinkhole at the beginning, so of course that's kind of the same idea. The way sinkhole form is the water, underground water dissolves carbonate underground. And you may end up with cavities in the soil that eventually, when the roof of the cavity is too weak, eventually let down, and you have this very significant holes that can open at once, and they are very hard to predict, and like pretty much impossible to predict or to know where they are, and so that can really be a concern. And so again, if you have a better understanding on the intricacies between the mechanics and the chemical reaction here, then you can try to maybe improve the management of this kind of hazard. Again, this is just a summary. So any material or many brittle porous material can exhibit this kind of breakage jerky compaction. So I'm at the end. Sorry, I've been a bit longer than I expected, but yeah. Anyway, so that's the conclusion. Just as a reminder, so we have this jerky compaction that happens in dry or under fluid brittle porous media, and that really affect the mechanics of the material. And just to mention, so that's really a more broader problem of all this kind of trying to understand this interaction between the chemistry, the mechanics, the hydrology of the material, and also you can add thermal effect, of course, if you are trying to understand soil, and in particular deep underground soil and this kind of thing for CO2 storage and this kind of idea. For example, the thermal effects are also very important. Thanks a lot for your attention, and I'm happy to take questions.
So there was a question in the chat from Ben. He said, in the experiment, how did you measure the local velocity at all the points along the central line?
Yes, so how is the local velocity? Right, so so that's actually a fairly common technique that is used quite a lot of time. So the way you do it, it's an image processing method where basically you compare. Sorry, I'm trying to get. You compare patches between frames. So basically, you take a sub portion of the image here. So maybe this middle part here, and you try to find it in the next image, right? And if you find it in the next image displaced for 10 pixels, let's say, then you know that your velocity of this patch has been 10 pixels divided by the frame time between the frame, basically. So that's called a particle image velocimetry. It's a very widespread technique. If you want to look it up, that's the name is this. And for those of you that are no, I don't know. It's definitely, it used to be taught in one unit, but I don't remember which one. Sorry.
So there's another question in the chat. So if anyone has any questions.
Does degradation, oh, yeah, can I take the next question?
Yeah, just go.
Yeah, so does degradation always happen? Sorry, my internet is a bit unstable apparently. Does degradation always happen at the bottom? Well, not necessarily. I mean, all the experiments we have done, indeed, the degradation, it's kind of easier to control when it happens at the bottom, but it doesn't have to, right? And definitely, naturally, there's no reason, because you can have seepage in pretty much all direction. And if you think about acid rain or something like that, for example, then you can have infiltration from the top. So it doesn't have to be from the bottom. It's just experimentally, it was a bit more convenient to do it like that. But we do want at some point to try different way to have the degradation, because that also affects the mechanics, right? It's not the same if you are going to degrade in the direction of your loading or perpendicular to your loading. So all these kind of three-dimensional effects in a way are also quite interesting.
Excellent answer. So I have a question here that about how your research affects a broad range of industries. You mentioned mining, but I also heard that agriculture and even pharmaceuticals is affected by your research into materials and brittle porous media.
Right. That's always a tricky question, I guess, for research that is a bit fundamental, I suppose. We are talking about long-term, I guess, effect on industry. So I wouldn't claim that what I showed today is going to affect industry in the next, let's say, 6 months or a year. But eventually, I think that's to know about this effect is important, because then we can. That's also, I guess, kind of our part of our role as academics to be able to say, oh, look, this phenomenon can happen, and if you don't know about it, you're not going to be able to consider it if you are doing a design or something like that. So I think that's this effect that can be interesting. And yeah, so I mentioned mining, pharmaceutical. I mean, as I mentioned, the compaction or the fabrication of pills through compaction of powders is really quite important, and there is a lot of complex physics in that kind of aspects. Yeah, agriculture, I'm not quite sure, but I'm sure I can find some kind of link with agriculture.
So there's another question in the chat. So could the dynamic compaction effects be as positive, at least locally high stiffness or strength can be achieved?
I suppose it could. I don't know if it would be quite like if it would be easy to control to get this kind of effect. It kind of, I mean, definitely it would be a way to at least, like if we are thinking of a material and things like that, having a little bit of breakage to just get rid of the very low strength grains or something like that can be useful, right? Because then I mean, if you have already gone through some breakage, then you have gotten rid of the weakest grain, and then your material overall should be a bit stronger. So I think that's definitely something that could be interesting. I guess in terms more of material, like material science, really. It could be something to think about. I agree. How does this apply to building bridges? Well, usually you build bridge on soil, so what I've been talking about is related to soil, so that's how it affects bridges. Would be my answer here.
So I have another question. You've been researching in this field for more than a decade. How has technology advanced during this time in terms of granular materials?
Yeah, that's one of the questions you sent me, I think, by email. So it was interesting. It made me sound old, I guess. But it's a bit hard to say. There's quite a few aspects. I think, I mean, there are several aspects. There's the aspect that the numerical part has advanced quite a bit, I would say, because we do have like higher computational powers, and at the same time a broader range of method to do computation. So I think this part in numerical simulation definitely is much more accessible to in that respect. And of course, there's also technological development in terms of analysis of material. And Benji, of course, says Xray. I was going to mention it, that yeah, there has been a lot of advance in imaging. So from Xray, definitely tomography, Xray tomography, neutron tomography, sorry. A lot of different techniques that maybe weren't as developed 10 years ago, I guess. So that would be my answer. One of the things that I do want to mention is that there's been a shift, I mean, in my opinion, at least, in a way, from experimental research to a much more numerical research, so really only with simulation. And I think that's something that, maybe if I can go a bit more philosophical, that's something we need to be careful and aware, and at the same time careful about, because as I mentioned in the beginning, like, simulations are just that, simulation. What you put in is what you will get out. If you don't do at some point experiment, or if you don't link that to reality, then you may be simulating something that is not at all representative of what you have. So really, for me, you have these three legs, I guess, for research, which is experiment, simulation, and theory, and this kind of merged together in a way to get information on your system. And it's important not to, in particular, you know, we are in lockdown, all the labs are closed right now, for example, so everyone is doing more numerical stuff. But I think it's important to keep in mind that that experiments have value and are very important to inform simulation and in the other direction as well.
Yeah, that sounds quite interesting. So Lewis said in the chat, have you tested this on non-homogeneous materials, granola, for example?
We haven't. We haven't. It would. We thought about it. But it's like the homogeneous is already quite tricky. We did try chocolate puffed rice, right? So the how is it, the Cocoa Pops, which are a bit stiffer, so they have a different different response. We haven't mixed them too much because it kind of makes things more difficult. But yeah.
So my next question is, going off like the Xray question, how has your research into Xrays revealed any knowledge used to strengthen granular materials?
Yeah, so the use of Xray, so I haven't shown any Xray here, as you have seen. We haven't used it too much on this particular project. But the advantage of Xray is really that you can see through the material. So that's very convenient for soils and for sand and all this kind of material because they are opaque, right? So you can't see through. So with X-ray, you are able to see through the material. So that's really the advantage. And so that has a lot of effect, because one of the issue is that here, so at least here we have a transparent container, so we can image from the boundary. But it does mean that we have a boundary, and boundaries are really, well, I don't want to say an issue, but are a location where the material is going to behave differently, just because, well, you have a different in stiffness between the boundary and the material, you have a different in geometry between the boundary and the material. So it's very, it's a very, or it can be a different behavior for the material near the wall from the material that is inside the sample. So X-ray really is a good way to avoid this issue by going through the sample and by imaging the whole sample inside as well. And then X-ray really, like in particular with all the tomography technique, where you can reconstruct the three-dimensional, like the full three-dimensional field of the material, are very beneficial in that respect, because that's information that has never been accessible before for opaque material. Because so that's really a whole new new development in a way, because you can really see in the material and get much more information into the behavior, and then make more model and develop the understanding. So, for example, like if I can give a specific example in the X-ray, so we do have an X-ray facility in the School of Civil Engineering, and we have been able to look at how grain orient under flow. And for example, Benji Marks had a project, and Daniel Diaz da Costa had a project where they were able to look at the orientation of steel fiber in fiber reinforced concrete. And again, the orientation of the fiber is linked to the strength of the concrete. So that has really a lot of application by using X-ray, which allow to see through concrete, which is of course opaque, right? You can see through with light. So that's just an example among a few others.
I think we'll have the last question for today, which is, what challenges did you face while conducting your research on these materials, and how did you overcome this challenge? Yeah, I mean, there's a lot of challenges, but I think that's the fun of research in general, that there's a lot of issues, like when you do experiment or simulation or modeling, it's really the same. You always you always have issues and things that don't work quite the way you would like, and that you need to push through it. That's and I think that's the main interest in research, that you do have to push through the challenges, and it's very rewarding, you know, once you overcome even an experimental issue, a technical issue, whatever the problems may be. It's really a nice a nice feeling to you know, to try to get this kind of things working. And then, I mean, there's many other issues which are more, I guess, logistics and things like that, but I'm not going to bore people here. I think it's more yeah, in terms of research, it's at the same time very very, how to say, challenging, because every single step can be very hard, because every single step you are doing it for the first time, right? But at the same time, it means that when you manage to solve a problem, then you're happy because you have solved the problem, and it's nice. I don't know if that answers the question. It was more. I think that was great. It's something all research people have struggled with, and I guess it's what makes it fun. Yep. So now it would be great if everyone could turn their cameras on so we could take a quick photo. And if Francois, could you please start screen sharing? Yep. Thanks. I'll just take a screenshot. Great. So thank you so much for your presentation, Francois. On behalf of everyone watching, I learned quite a lot and I really appreciate you taking your time out of your busy schedule for this. If you haven't already, please fill out the sign-up form. And there's also an optional feedback form that you can do, and I'll put the link in the chat. Also, next week this week on Wednesday, we have a talk from Chris Bulmer about I Build mentoring program, which will be from 5 to 6, and it's the second package in the employment package. Next week, we also have trivia, so go check that out. But yeah,